Bible tells us of a time in which everything that is familiar to us will pass away, and there shall be a new heavens and a new earth. Well, that prophetic vision may well apply to the end of time, but only with a little bit of stretching. It applies to the tremendous changes that occurred in astronomy and physics in the scientific revolution, particularly around the year 1600, when the three characters that we're going to talk about in this lecture all lived. These three characters are first Tycho Brahe, then Johannes Kepler, and finally Galileo Galilei. Let's start with Tycho. Tycho Brahe was born in 1546, so 3 years after the publication of Copernicus's De Rev, if you want to put him in that context. He lived until 1601. Well, he's known as the most precise, and in fact the last of, the naked eye observers, the naked eye astronomical observers. His volumes and volumes of observations provided keys to several important discoveries about the structure of the heavens. Well, who was Tycho? First of all, Tycho was a member of the Danish nobility. If you are familiar with Shakespeare's Hamlet, you may remember the characters of Rosencrantz and Guildenstern. Tycho's actually related to them. As part of the Danish nobility, part of his astronomical program was made possible by a grant that he received from the king. He was given the island of Hven, which is a small island in the Danish Sound, northeast of Copenhagen. Here on this island, Tycho built his observatory castle beginning in 1576. Now, this castle was, in a sense, a multi-purpose center. First of all, as a member of the Danish nobility, he needed a manor house, so it was his manor house. It was also his observatory. There were places to make observations both in the castle and on the grounds. And he also conducted experiments in Paracelsian medicine there, the preparation of Paracelsian medicines, and on alchemical experiments. So he did quite a lot there at Uraniborg, which was the name of his castle. Uraniborg meaning it's a strange combination of Danish and Greek, the castle of the heavens. Tycho carried out observations there for decades, and he was assisted by a large number of students. How did he actually make his observations? Well, he had a large number of very precise instruments made. Remember, this is before the telescope, so it's all naked eye observation. He used things like quadrants. This is a quarter of a circle affixed to a wall. The wall runs exactly, let's say, north-south. There is a line to the meridian. And you can, by moving a sight that's pivoted, measure the altitude of a planet or star as it crosses the meridian. That's one kind of observing tool. This is a little bit more complicated than it sounds. It's not just moving a pivot and reading off a number, because you have to correct for atmospheric refraction. When a ray of starlight enters the Earth's atmosphere, particularly if it's obliquely, it gets refracted. And so the altitude that you actually see it at is actually a false reading. It's a reading after refraction. So Tycho had to correct for the effects of atmospheric refraction, which can be quite substantial, actually. Well, several of the specific observations that Tycho made pointed out certain deficiencies in the Ptolemaic and Aristotelian view of the cosmos. The first one happens in November of 1572. Tycho is busy working out the prognostications for 1573. Remember, we think of Tycho as a naked eye observer, as an astronomer, but of course he was interested in astrological prognostications as well. In November of that year, according to him, he comes out of his laboratory and he looks up and he sees a new star in the constellation of Cassiopeia. A new star? Well, if you're making a prognostication, what does it mean when suddenly a new star appears in the heavens? More importantly, he and others found that this star was further away than the moon, using parallax, in this case using diurnal parallax. That is, you take a measurement, you look at the heavens at a time early in the evening, and then one just before dawn. The Earth has rotated a considerable distance. or the heavens have revolved a considerable distance, depending on your cosmological system. The two situations are observationally equivalent. You can see a parallax of the moon this way. So you observe at two different vantage points and look for change, just like the thumb held at arm's length, looking at it with your two different eyes. This means that there's change in the heavens, contrary to Aristotle. Remember, Aristotle said the superlunary realm was an eternal realm. It was a realm without change. The same thing happens in a different way in 1577 and 1585. In each of those years, a bright comet appears, and Tycho and others find that it has a smaller parallax than the parallax of the moon. Therefore, it's much further away than the moon is, it's in the heavens, and a change has occurred. Aristotle said that comets were a terrestrial, an atmospheric phenomenon. They were the ignition of vapors coming up from the Earth. But Tycho and other astronomers in late 16th century show that the comets are much further away. Tycho also finds that the path of the comet had to take it through the sphere of Mars, meaning that the planetary spheres cannot be solid objects. Because here's an example of an object that has crossed from one side of the sphere of Mars to the next. Well, there are the ways that Tycho presented information that was at variance with with Ptolemy and Aristotle. Did he adopt Copernicus? Well, remember, very, very few people adopted Copernicus. Tycho was not one of them. He rejected heliocentrism. He rejected the idea of a moving Earth as physically absurd and theologically untenable. It's theologically untenable because if you'll remember in the Old Testament, during a battle, Joshua, through the action of God, makes the sun stand still. And it says, "Stand thou still, O sun." It doesn't say, "Stand still, O earth." The sun is stopped by Joshua. Therefore, the sun must be the thing that's in motion, not the earth. So Tycho, taking a literalist stance, thinks that Copernicus is theologically untenable. In 1588, however, Tycho presents his own solution, a solution to the structure of the cosmos that follows neither Ptolemy nor Copernicus. He retains the Earth at the center, immobile. The moon goes around the Earth. The sun, likewise, goes around the Earth. But all the other planets have the sun as their center of motion. So there are two centers of motion in the Tychonic system, whereas there's only one in Ptolemy. There are actually two in Copernicus because the moon goes around the Earth as well. But for Tycho, all the planets orbit the sun, but the sun orbits the Earth, as does the moon. Now we have three systems to choose from: Ptolemaic, Copernican, and Tychonian. Let's check out our next character, Johannes Kepler. Kepler is younger than Tycho. He's born in 1571. He lives until 1630. Students today still learn in fundamental astronomy and physics classes Kepler's 3 laws of planetary motion. Now, a historian of science seeing something like this wants to know more than just what the laws say. What the laws say is important, but what a historian of science really wants to know is how were they discovered, why were they discovered, and most importantly, what's their original context? Things like this tend to be taken out of context all the time. What's the context for Kepler's 3 laws of motion? Well, let's find out. Let's start with Kepler's education. His first teacher of astronomy was Michael Maestlin, who was at the University of Tübingen. Maestlin is one of the few convinced Copernicans of the 16th century, and he relays that certainty about the truth of the Copernican system to his student Kepler. Well, after Kepler finishes his education, he gets his first job, teaching at the Lutheran school in Graz in Austria. There, something very important happens to him. It's so important he records the exact date. On the 19th of July in 1595, he's lecturing to his class on what are called the fiery trigons. These are These are related to the conjunctions that happen every 20 years between Saturn and Jupiter, the so-called Great Conjunction. Astrologically, very significant. What he had done was to draw a circle, and then he started drawing the circle of the zodiac, then started drawing triangles that were slightly offset one to another inside of it. After he finished drawing these triangles, he realized that at the center, he had created a new circle with a different diameter. This gave him an idea. Can we explain the distances of the planets by simple mathematical harmonies? And so he set to work on this. First, he tried simple numerical ratios, and that didn't work. Then he tried ratios of polygons, inscribing them in circles, circumscribing circles around them. That didn't work either. Finally, he tries, instead of polygons, polyhedra. And he focuses on the 5 perfect solids, the 5 platonic solids, the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. And he finds the answer he's looking for. The 5 nested platonic solids, nested one within the other, explain for him not only why the planets are at the distances they are from the sun, but also explain why there are exactly 6 planets, because there are only 5 perfect solids, and the 5 perfect solids act as dividers. Let me explain that again. It's a little hard to visualize this. Kepler takes the Earth's orbit as his starting point. He circumscribes the Earth's orbit with a dodecahedron, that 12-sided perfect solid. He then circumscribes the dodecahedron with another sphere. That sphere gives him the distance for Mars. Outside of that, he circumscribes that sphere of Mars with a tetrahedron. Circumscribes another sphere outside of that. That sphere gives him the distance for Jupiter. A cube, a sphere, gives him Saturn. Then he goes back, puts inside the Earth's orbit the icosahedron to get the sphere of Venus, and then the octahedron to get the sphere of Mercury. What he says here, let me quote him, is he says, God, in creating the universe and regulating the order of the cosmos, had in view the 5 regular solids of geometry, as known since the days of Pythagoras and Plato. Here is clear evidence to a return to the ideals of Plato's Timaeus. Remember, Plato's Timaeus has the demiurge creating the universe, looking at mathematical models, looking at the ideas. The whole universe is orderly and harmonious. And here, Kepler is showing the same kind of thing. As he says, nothing is fashioned by God without a plan. Well, Kepler's ideas were presented in the Mysterium Cosmographicum, the cosmographical mystery, or the secret of the cosmography. 1596, this is published. Kepler sends out several copies of the book. One goes to Tycho, who's impressed and invites Kepler to come and work with him at Uraniborg, but Kepler declines. He eventually did work with Tycho in 1600 when Tycho moved to Prague to the employ of the Holy Roman Emperor Rudolf II, after Tycho's relationship with the new Danish king became a bit sour. After the Mysterium Cosmographicum, Kepler begins working on explaining why the planets move and constructing a planetary system. He's already answered the question, why are there 6 planets? There have to be 6 because there are only 5 platonic solids. Not a question we'd ask in modern science. Nonetheless, it's a question that Kepler asked. Why do the planets move is his next question. He postulates the idea of what he calls an anima motrix, a moving soul or a motive soul lodged in the sun that pushes the planets around in their orbits. Think of it sort of as a turning paddle wheel, and this anima motrix pushes the planets around in their orbits. He also says something to deal with the problem of Aristotelian physics, saying the Earth has to be at the center. He says, no, things just attract their like, and so if we pick up a piece of Earth, it naturally falls back towards the Earth because they're alike. He says if we took two stones and we put them way out in space, far from the Earth, they would have a sympathy and they'd move towards each other because, again, they're alike. Now, these ideas he takes from contemporary developments in magnetism, and we'll come back to them in due course. But then he does another thing. He tries to produce a system of the cosmos working first on the motions of Mars. Mars is a problem planet. Its motion is more difficult to explain than the others. What he finally comes down to is he postulates what we now call his first law. The planets don't move in circles. They move in ellipses. And the sun is at one focus of the ellipse. Now, this is a dramatic move. We might not think about it as such, but what's Kepler doing? He's discarding a 2,000-year-old, older than 2,000-year-old tradition of using circles as the perfect orbit, the orbits that have to be used to explain the planetary motions, uniform motion. This is a big moment, but how does Kepler get beyond it? Well, he argues that I couldn't do anything else. Only the ellipse works, and the ellipse gives us much better prediction of the places of the planets. What he also finds out is that the anima motrix, the idea of the anima motrix, helps him retain some kind of uniform motion in the heavens. He finds that the planets, when a planet is furthest from the sun, it moves more slowly. When it's closer to the sun, it's moving faster. This gives him the idea of his second law, the so-called equal area law, that a planet moving, let's say, for a day, any fixed period of time, sweeps out an equal area of its orbit. So that is, when it's further from the sun, it's moving more slowly. It's further away from the anima motrix in the sun, so the effect is less. So it moves more slowly. It sweeps out a sector that's long and narrow. Narrow because it's moving slowly. When it's closer to the sun, it's moving much faster. And so the sector it sweeps out is wider but shorter. The area of the two sectors, however, remains the same. That's his second law. It allows him to retain the idea of uniform motion. The uniformity is not the speed of the planet or the motion of the planet, it's the area of its orbit. It sweeps out. Now, I should mention, before I go any further, an astronomical fact. These ellipses that Kepler was using were not very far off being circles. If you draw a big circle and a big ellipse, which represents the orbit of Mars, and if I held these up for you, you would have to look very closely to see the difference. It makes a difference in the planetary positions, but it's not like textbooks show it with this great eccentric ellipse with the sun way at one end. Remember, these are very close to being circles, actually. All right. What does Kepler do next? Well, he publishes the Astronomia Nova, the new astronomy, in 1609 that talks about the ellipse and the equal area law. He then produces, 10 years later, the Harmonices Mundi. This is in 1619, which contains his third law. This law is a little bit more difficult to think about, so let me read it slowly. He says that the square of the period of a planet's orbit, the time it takes to go around the sun, the square of that period is proportional to the cube of its mean distance from the sun. That's his third law. Well, again, context is crucial. This is one law, one proportionality out of many, many proportionalities which are described in the Harmonices Mundi. The context is that the book is all about finding harmonic ratios in the cosmos. It's an expression of a Christianized Pythagorean Platonic cosmology. The Platonic solids, the Pythagorean music of the spheres, and other numerical relationships all show up in this book. The real subject of the book is the harmony of the cosmos, revealing God as the geometer. Let me read you another quote from Kepler, writing in a letter to his teacher Mestlin. He says, "I wanted to be a theologian. For a long time I was troubled, but now I see how God is also praised through my work in astronomy. So there's an inherently religious character to Kepler's search for the harmonies of the cosmos. Let me point out that even though the third law sounds like a very technical scientific law, it sits in the Harmonices Mundi alongside staffs of music where Kepler tries to plot the melody of the spheres, the music that the various planets make in their orbits. So it's very far removed from the context in a physics textbook that this third law has now. The three laws were in fact extracted from their context later in the century by Isaac Newton, and the deeply religious and metaphysical mathematical basis of their discovery and enunciation was lost. That's what we have to do in the history of science. We keep trying to put that context back to see where scientific ideas come from. And as you can see here, it's often rather surprising. Prepare to be surprised a little bit more yet to come. Well, remember I said that Kepler sent his Mysterium Cosmographicum to Tycho. Well, he sent it to other people as well, including to a little-known professor of mathematics at the University of Padua by the name of Galileo Galilei. Galileo was born in 1564. He lived until 1642. So his death date corresponds with the 100-year anniversary of the publication of De Revolutionibus. Galileo's contributions to the history of science fall both within the realm of astronomy and of physics. In this lecture, I'm going to talk about his astronomical contributions. The next lecture will look at his physics. Well, in 1609, the same year that Kepler announces the use of ellipses for planetary orbits, Galileo constructs his first telescope. He's not the inventor of the telescope, but he is the first person to apply it to astronomical observations. In the winter of 1609 and 1610, he makes several important astronomical discoveries in very short order, quite remarkable. And these were published in a book he entitled The Sidereus Nuncius. There are two ways to translate that title. It can either be The Message of the Stars or The Starry Messenger. So either message or messenger. Short little book, but very influential. What are some of the things he mentions in it? Well, first of all, he turns his telescope on the moon. Big, bright object, good thing to look at. He finds that the moon is covered with mountains and valleys and oceans, what we still call the seas, the maria in Latin, the seas of the moon. He thinks they're water. It seems then that the moon is made out of the same stuff that the earth is made out of. Quite contrary to Aristotle, who said that all the heavenly bodies are made of the quintessence. The superlunary realm, the realm of the eternal quintessence, has no change in it, nor does it have the mixtures of the four elements. But the moon looks just like the earth. He then turns it to the planet Venus, another very bright object in the morning and evening sky, and finds that the planet Venus, like the moon, shows phases, full, crescent, gibbous. Therefore, it must sometimes be between the earth and the sun, and sometimes on the opposite side of the sun from the earth. This can't happen in Ptolemy's system. There's no way that Venus would show this kind of phases in the order it does with Ptolemy's system. It means either Copernicus's system or Tycho's system has to explain these phases of Venus. Then he turns his telescope as well onto the planet Jupiter, another very bright nighttime object. And he sees four tiny points of light arranged on either side of the disk of the planet Jupiter. From night to night, as he watches, the positions of those four little dots changes. And he concludes that what he's seeing are four moons, four satellites of the planet Jupiter. This means that there must be another center of motion in the heavens. Here are these moons going around Jupiter, meaning not everything goes around the Earth or around the sun. It gives a precedent for the multiple centers of motion that are necessary in Copernicus's system or for that matter, in Tycho's system as well. But Ptolemy's system, Aristotle's system, don't work very well with the satellites of Jupiter. Now, at a later point, Galileo also watched sunspots. He claimed that if you watch these sunspots from day to day, they move across the sun's disk, they change their shape, they disappear, and they reappear. This means that, first of all, the sun is rotating, just like the Earth is supposed to do in Copernicus' system, and also there's change and corruption in the heavens, contrary to Aristotle. Aristotle's not making out very well here with the telescope. Well, he does one other thing. He names these moons of Jupiter the Medicean stars. He names them after Cosimo de' Medici, the Grand Duke of Tuscany, and as a result attracts the patronage of the Grand Duke and a very well-paid position in his court. We've since renamed these satellites the Galilean satellites in honor of their discoverer. Well, in my last few minutes, I need to say a little something more about the telescope, because Galileo's use of the telescope brings up the problem of instruments in the scientific revolution. Instruments that help and extend our senses. The most clear examples are the telescope and the microscope. The validity of observations made using these aids to the senses was a hotly debated topic. How valid is telescopic information? We may think that's a little bit strange. Well, you look through the telescope, what's the difference of light coming through a telescope or coming into your eye? That's a modern perspective, because we're on the other side of the debate. We're on the debate after it's been solved. In Galileo's time, this debate was very much ongoing. Many critics claimed that Galileo's observations were actually artifacts of the instrument. On the one hand, they had some basis for this, because the lenses were poorly ground, the principles of aberration were not understood optically, and so often if you take a cheap telescope of the style Galileo used and point it at a distant light source, a candle across the room or something, you often will see these little multiple images on either side, which look like the Medicean or the Galilean satellites. Moreover, lenses had been used since the Middle Ages, like mirrors had been used since the Middle Ages, for deception, for deceptive magic, to make false images appear. So how do we know that these images we're seeing aren't part of this sort of deceptive optical phenomenon that lenses and mirrors were known to be used for? Well, the matter was put before the Jesuits of the Collegio Romano, their college in Rome, and the Collegio Romano actually came out on Galileo's side partially. They agreed that Galileo was seeing what he claimed to see. There were these 4 points around Jupiter. Venus did have phases. There are things that look like mountains and seas and valleys on the moon. There are spots on the sun. In fact, it was a Jesuit, Christoph Scheiner, who may well have seen the sunspots and observed them first before Galileo. Galileo has a very unfortunate argument, rather violent argument with Scheiner over this issue. But the Jesuits say his interpretations may not actually be right. He's seeing what he's seeing through the telescope, but we don't know about the interpretation. That may not be true. Well, instruments continue to play an increasingly important role in the history of science. Much of big science nowadays would be totally impossible without the constant use of instruments. And here's the period where instruments to extend human perception really start coming in to the practice of science. You can argue that Tycho's instruments, since they're only using the eye and it's just sort of measuring what the eye is seeing, isn't really affecting our vision much. But once you use a telescope, or nowadays things like electron microscopes, how much is it really showing? What's an artifact of the instrument? It's a difficult philosophical problem. The other philosophical problem is, whereas instruments are supposed to enable us to see more, to sense more of the natural world, in one way they actually separate us from the natural world, because there's something intervening, there's something interposed between us and the natural world that does something we can argue about what it's actually doing, but it's separating us, in a sense, from the natural world. So there are a lot of philosophical issues that have to be worked out about instruments. Well, despite all of that, one thing that we can see is that Galileo's use of the instrument, interpreted the way Galileo wants to interpret it, does quite a bit of damage to the Aristotelian worldview, to the Ptolemaic worldview. What Galileo and his contemporaries have to do is provide some positive alternative to Aristotle, a new physics as well as a new astronomy, a physics that can undergird the new astronomy. We have to figure out how the world actually can be functioning. Well, Galileo's most important contributions, arguably enough, are in physics, in fact, and in the next lecture, we're going to take a look at what they are.